Welcome to an Institute of Mathematics and its Applications video on numerical solutions of algebraic equations, or searching for your roots. Some equations can be rearranged to get a direct answer for the parameter of interest, but many cannot. We solve the latter numerically using iterative methods. That is, we guess an initial answer and use this to find an improved answer. Then use this as the next guess, repeating the process until we are satisfied the result is close enough. In this video we look at four methods for doing this: simple iteration, also known as fixed point iteration, bisection, linear interpolation, also known as the method of false position, and Newton-Raphson iteration. In each case we construct an equation of the form f of x equals 0 and try to find a value of x that satisfies this equation. Such a value is known as a zero, or root, of the equation. Where might these methods be needed in the wider world? Let's have a look at a few examples. We might need these methods when finding the shape of structures in engineering, setting annuities and interest rates in finance, plotting the paths of comets in astronomy, reconstructing brain images from CT scans in medicine, designing circuits in electronics, calculating properties of gases in chemistry, and others too numerous to mention. We'll use some of these to illustrate our four numerical solution methods. Let's start with an engineering example to illustrate the simple iteration method. Suppose we want to find the point of maximum deflection of a uniform beam, simply supported at one end and fixed at the other, subject to a linearly increasing distributed load. The vertical deflection y, as a function of horizontal distance x, is given by this expression, where everything on the right-hand side except x is a constant. The general shape looks something like this. At the point of maximum deflection, the gradient is 0, so we need to construct a function for the gradient and then find a value of x that makes this 0. A word of caution: the gradient at the fixed end of the beam is also 0, so we need to be careful to check we get the solution we want. The equation for the shape of the beam might look a little complicated, but it's basically just a straightforward polynomial, so it's easy to differentiate to find the gradient as a function of x. The gradient is 0 when the term in parentheses is 0, so we construct the function f of x, shown here, and set this equal to 0. For our purposes we don't need to know the true values of the distances, so we set the beam length L to unity. In effect, this means we can interpret x as the fractional distance along the beam. For the simple iteration method, we now need to rearrange the equation to be of the form x equals g of x. That is, we want to isolate a single x on one side with everything else, including other x's, on the other side. There are several possible ways of doing that here. Let's look at two of them. One possibility is to rearrange as 6x squared equals 5x to the fourth plus 1. Divide through by 6 and take square roots. Another is to rearrange as 5x to the fourth equals 6x squared minus 1, divide through by 5 and take fourth roots. In both cases, on the right-hand side, we use the value of x at the nth iteration to give us the next n plus 1th value. And of course we have to start with an initial guess for n equals 1. Let's try this for our first rearrangement with an initial guess of x1 equals 0.4. Plugging this into the right-hand side here, we get x2 is 0.434. Plugging this in turn, we get x3 0.443, and so on. Listing the results of several iterations, we have x is 0.4, 0.434, 443, and so on until we get to 0.447. So our root is 0.447 to 3 decimal places. We can visualize the process in the form of a staircase diagram. We put the nth value of x on the red line, and the n plus 1th appears vertically above on the blue line. We read that across horizontally to the red line to repeat the process and continue to convergence. Let's try the same thing for our second rearrangement with the same initial guess of x1 equals 0.4. Putting this into the right hand side, we get x2 is, oh dear, a complex number. That's no good. We want distances to be real numbers. How did that happen? Well, if we look at the numerator inside the parentheses, we can see that if 6x squared minus 1 is negative, we'll get a complex number when we take the fourth root. So let's try a different starting value. We now have a real number for x2. Plugging this in turn gives x3 another real number. Looking at the results of several iterations and illustrating this with a staircase plot, we get this. This isn't converging on the same value we found previously. It seems to be converging on 1 rather than 0.447. This is in fact a perfectly valid solution to our equation, but it represents the fixed end of the beam rather than the point of maximum deflection. This highlights the importance of checking that any solution we get from the mathematics represents the solution we actually want. As an aside, we should note that convergence doesn't always follow a staircase pattern. Depending on the shape of g of x, that is the function that represents the right-hand side of our iteration equation, the iteration steps can wind around the point of convergence, creating what is known as a cobweb plot. And we also need to be aware that our iterations might not converge at all. Both cobweb and staircase diagrams can shoot off to infinity, depending on the form of g of x. Loosely speaking, to ensure convergence, we want the absolute value of the gradient of g of x to be less than 1 in the region of our search. Moving on to the bisection method, we'll use the example of finding the position of Halley's comet sometime after it's passed its perihelion point. Perihelion is its position closest to the Sun. Halley's comet has a very eccentric orbit. It's a very flat ellipse. It's shown here in red. This diagram is not to scale. If it were, the red orbit would be a lot flatter. Astronomers like to use a representative circle. Shown here is a blue dashed line to find the position of the comet. They use Kepler's equation, which is E minus epsilon times sine E equals m, where epsilon is the orbit eccentricity, a number between 0 and 1. For Halley's comet, it's 0.967. M is known as the mean anomaly, and E as the eccentric anomaly. For anomaly, read angle. M and E are angles. Astronomers call them anomalies for historical reasons. M represents the angle obtained as a time fraction of a complete rotation. The fraction is the time lowercase t after it passes perihelion divided by the time uppercase t for a complete rotation. E is the corresponding angle on the representative circle. If we choose a time, say 25 years after Halley passes perihelion, we can immediately calculate the anomaly or angle m, but we want to know the corresponding anomaly or angle E. To do this, we need to solve Kepler's equation numerically, which we will do here using the bisection method. Here are the values of eccentricity, period and time after perihelion that we will use. These allow us to calculate m immediately as 2.067 radians. You rewrite Kepler's equation like this and define the function f of x. I've changed the notation and replaced the parameter of interest e with x, simply but to maintain a consistency of notation in each of our iteration methods. And of course, we're looking to find the value of x that makes f of x equals 0. In the bisection method, we first need to identify two values of x such that the corresponding values of f of x straddle the root. Let's try x equals 1. This is negative. If we have x equals 2, this is also negative, so we can't take both 1 and 2 as starting values. Let's try x equals 3. This is positive. So, as f of x is continuous between x equals 2 and x equals 3, there must be a value of x between 2 and 3 where f of x is 0. Using x low equals 2 and x high equals 3 as starting values, we now choose the average of those two, the midpoint 2.5, as our next value. Since our function of 2.5 is negative, we know that the root must lie between x equals 2.5 and x equals 3. So we replace x low with 2.5 and repeat the process. Let's see this in action. In 8 steps, we get close enough to f of x equals 0. Here's a list of the steps, with the successive values of the low, high and middle values of x, and the signs of the corresponding function values. In the first step, the sign of f of x middle is negative, so for step 2, x low is replaced by x mid. The new x mid is calculated, and the sign of the function of this new value is found. In this case it's positive, so in step 3 x high is replaced by x mid, and so on until we find a value of x for which f of x is close enough to 0, or successive values of x are the same, to whatever precision we're interested in. Remembering that here x represents the mean anomaly E, we can say that 25 years after comet Halley passes its perihelion, E is 2.582 radians, whereas the mean anomaly M is 2.067 radians. If you prefer your angles in degrees, then E is 148 degrees, while M is 118 degrees. We'll continue to use Halley's comet to illustrate our third numerical solution method, that of linear interpolation. So we start with the same function, f of x equals x minus epsilon times sine x minus m, for which we will look for the value of x that makes f of x 0. We start in a similar way to that for the bisection method. That is, we choose two values of x that straddle the root. This time, however, instead of just looking at the signs of the function f of x, we make use of the two values of f of x. We get the next value by linearly interpolating between these two values. We call it xfp, the fp standing for false position. By considering the two similar triangles in the right-hand graph, we have fx high minus 0 divided by x high minus xfp equals 0 minus fx low over xfp minus x low, and we can rearrange that to get x of fp. If the new function value is positive, we replace x high by xfp for the next iteration. If it's negative, we replace x low by xfp. We might as well choose the same starting values, x low equals 2 and x high equals 3, that we used previously. This time we get close to the root in just 3 steps. Looking at a summary of the values at each step, we see that the first value of f of xfp was negative, so xfp replaced x low for the second iteration. The same was true for this iteration, and the third iteration produced a value of xfp close enough to 0 for us, to 3 decimal places here. Here again is the resulting value of the eccentric anomaly or angle E. In this case, the linear interpolation method required fewer iterations to find the root than did the bisection method. However, it's a mistake to think that that is always the case. Sometimes the bisection method is faster. For our last method, Newton-Raphson iteration, we will use an example from the chemistry of gases. You might know that the equation of state for an ideal gas is PV equals RT, where P is pressure, V is volume, T is temperature, and R is the universal gas constant. However, real gases don't always behave like an ideal gas, and for many situations the van der Waals equation of state is better. Here is van der Waals equation of state, expressed for 1 mole of gas, in terms of normalized values of pressure, volume and temperature. That is, the values of pressure, volume and temperature are expressed as fractions or multiples of their values at the critical point. At the critical point, there is no distinction between gas and liquid. We can rearrange this equation so that the right-hand side is 0. We'll set values for P and T and then search for the corresponding value of V. So we'll define function f of x as here, where, as before, for consistency of notation, we'll use x in place of v for the parameter we iterate on as we try to find the value that makes f of x equal 0. In the Newton-Raphson method, at each stage we have a single value for x, xn, at which we find the gradient of the function f of x. We extrapolate the gradient until it hits 0 and take this point as our new value of x, xn plus 1, for the next iteration. We repeat this until we're as close to fx equals 0 as desired. We can see from the diagram that the slope at fxn is given by f primed xn equals fxn minus 0 divided by xn minus xn plus 1. Rearranging this, we have the next iteration value as xn plus 1 equals xn minus fxn divided by f primed xn. In our case, the function is as we have here. We can differentiate this to get the gradient here. Let's double the temperature, that is, make it twice the critical temperature, and keep the pressure at 1, that is, keep it at the critical pressure. Since the volume is likely to increase under these conditions, let's initially assume that the volume will double at the critical volume. In other words, we'll set x1 equal to 2. Plugging this into the Newton-Raphson iteration expression, we get x2 is 3.239. This in turn gives x3 equals 4.447, and so on. Continuing this, we see that after 5 iterations the function is 0 when x is 5.117. In other words, with the temperature at twice the critical temperature, while the pressure stays at the critical pressure, the volume rises to 5.117 times the critical volume. You should note that there are situations where the Newton-Raphson method doesn't work. With the sort of curve shown here, for example, the iterations wind round the root at ever-increasing distances from it. However, when it does work, it tends to do so relatively rapidly. That brings this video on numerical solutions of algebraic equations to an end. For further interesting aspects of mathematics, visit these websites.